Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, where are you? Where am I? Here I am. Hello. Lesson 34, review of the assumptions. This is the last lesson in Module 1. A great review. Everything you need right here on 2 pages. So here we go. So we have an assumption, a fact, or a property in the first column, guiding questions, applications in the middle, and then your notes and solutions are on the right column. First one says, and these are classworks, by the way, so you should be pausing the video, trying these on your own, and then checking to see if you did it correctly. So given 2 triangles, ABC, and A prime, B prime, C prime, so that AB equals A prime, B prime sides, the measure of angle A equals the measure of angle A prime, an angle, and AC equal to A prime C prime. And notice that there is an A in the name of this side and an A in the name of this side. So angle A is included. Then the triangles are congruent by side, angle, side. Okay, so guiding question. The figure below is a parallelogram. A, B, C, D. They're talking the whole thing. So they have opposite sides marked as parallel since it is a parallelogram. Okay, what parts of the parallelogram satisfy the SAS triangle congruence criteria for triangle ABD, which does not exist yet, and triangle CDB, which does not exist. Describe the rigid motions that map one onto the other. Consider drawing an auxiliary line. So I'm going to draw that said line, which is BD. So there's BD. Okay. So to solve this, the first thing we will do is we're going to say that AD equals CB. Okay, so I'm going to mark my diagram. AB equals CD, and that's a property of a parallelogram. If you have a parallelogram, opposite sides are congruent. So I have AB equal to CD. Now notice we're talking about this triangle up here, so let me now make it thinner, but the same color. We are talking about this triangle here and this triangle here. Okay, we're trying to prove that these 2 triangles are congruent. The blue is congruent to the red. Okay, so we now have a side in each triangle. The next thing we're going to do is we now have angles congruent. The measure of angle ABD, which is right here, is congruent to the measure of angle CDB, which is right here. And the reason is alternate interior angles. Since we have parallel lines and BD is a transversal, we have alternate interior angles that are congruent. So now we have a side equal to a side, an angle equal to an angle. We're just lacking that last side, and that is the easy one of my favorite properties, reflexive. BD is equal to itself. So BD is equal to itself, reflexive property. And then finally, we can now state that the triangles are congruent. Triangle ABD is congruent to triangle CDB by the side angle side. Okay, and then it says, describe the rigid motion. So if I put a dot at this midpoint here, and if now I can't do this the right way. I'm not allowed to, this program does not allow me to rotate from the center. But if I grouped and made this triangle, if I rotated that 180 degrees, but I kept the center of BD where it was, now you see the blue landed right on top of the red. So it is a 180-degree rotation around the midpoint BD. And there's problem number 1. All right, let's move on to the second one. Given two triangles, ABC, in the diagram, ABC, no, not the diagram yet. Given two triangles ABC and A prime, B prime, C prime, if the measure of angle A equals A prime, an angle, AB equals A prime, B prime, a side, and the measure of angle B equals the measure of angle B prime. Now notice here, we have an angle A, we have an angle B, we have a side called AB, which is both vertices labeled. That means that the side is included. Then the triangles are congruent by angle, side, angle. And we can see that just from this sentence that AB is an included side because A is an angle and B is an angle that make that side AB. In the figure below, triangle CDE, this bottom triangle, is the image of the reflection of triangle ABE across segment FG or line FG. Which parts of the triangles can be used to satisfy the ASA congruence criteria? So the first thing we're going to do is say that the measure of angle AEB, and I will label it AEB, is equal to the measure of CED, which is right here, because AD is a straight line, BC is a straight line, and we have vertical angles congruent. Okay, so vertical angles are equal in measure. And then we're going to say BE equals DE. BE equals DE. Reflections map segments onto segments of equal length. That's the definition of a reflection. You reflect a segment across FG, the reflection is going to be the same length. So they are congruent. And then I keep going and I say the measure of angle B is congruent to angle D. Reflections map angles onto angles of equal measure. So now we have angle B right here and angle D right here. So we have an angle, an included side, an angle, an included side, an angle. So now we can jump right to it and say that the triangles are congruent by ASA. Okay, moving right along. Let me extend the page and move this up. Okay, given two triangles, ABC and A prime, B prime, C prime, if AB equals A prime, B prime, a side, AC equals A prime, C prime, a side, and BC equals B prime, C prime, another side, then the triangles are congruent by side, side, side. So in this diagram, we have a triangle ABC. ABC is right here, and ADC right here. And they're formed from the intersections and center points of circle AC, A and C. So we draw a circle A with radius AB, and AB is equal to AD because radii are equal to each other, and that's how this is all going to come together. I'm getting ahead of myself. Okay, so prove that triangle ABC is congruent to triangle ADC by using side, side, side. So the first thing we're going to do is AC is a common side. In other words, AC is in both triangle ABC and triangle ADC, and therefore it is congruent to itself by the reflexive property. And then AB equals AD, and that's what I stated a moment ago. AB is this segment here that is congruent to AD. And the reason is they're both radii of the same circle. No matter where we draw from A to the circle B, that distance is the same everywhere. That's what creates a circle. The definition of a circle is the set of all points equidistant from the center, A in this case. Okay, so AB is equal to AD. So now we have a side, we have another side. And then finally we have BC equal to itself because they're both radii of the bigger circle C. So I can label that side right here equal to this side right here because they're both radii of circle C. Okay, And therefore, thus, triangle ABC is congruent to triangle ADC by S, S, S. Page 2 continues with this really useful table that just puts this whole first module together nicely. So it says, given two triangles ABC and A prime, B prime, C prime, if AB equals A prime, B prime, that's a side. Angle B equals the measure of angle B prime is an angle, and the measure of angle C equals the measure of angle C prime. Now notice the side's called AB, and we have angles B and C. We don't have angles A and B, so it's not an included side. It's two angles in a side that's not included. That's AAS, and they are congruent. So the angle side congruence criterion is essentially the same as the angle side angle criterion for proving triangles congruent. Why is this true? Okay, so they're saying AAS is the same as ASA. Why is this true? Okay, so this is not asking us to prove anything. So it's true. It says, if two angles of a triangle are congruent to two angles of a second triangle, then the third pair must also be congruent because of the triangle sum theorem. If I have an angle that's 90 degrees and another angle that's 90 and an angle that's 20 and another angle that's 20, well, that adds up to 110 degrees. So the third angle must be 70 in both triangles to total 180. Therefore, if one pair of corresponding sides is congruent, we treat the given corresponding sides as the included side, and the triangles are congruent by ASA. So we're just choosing a different side in that case. Hopefully that makes sense to you. Okay. A lot of writing, so if you didn't get this, pause the video and I'll continue. Given two right triangles ABC and A prime, B prime, C prime with right angles angle B and angle B prime, if AB equals A prime, B prime, a leg, and AC equals A prime, C prime, the hypotenuse, and angle B is the right angle, then the triangles are congruent by HL or hypotenuse leg. In the figure below, CD is the perpendicular bisector of AB, all right, which means two things. Where's my pen? Perpendicular means forming right angles. So angle ADC is a right angle and angle CDB is a right angle. And if it's a bisector, AD is congruent to DB. So just that statement alone, perpendicular bisector forms two segments that are congruent and two right angles. Okay, and it says, and triangle ABC is isosceles, which means AC is equal to BC. Isosceles means two sides are congruent, and the altitude can't be equal to half of one of these sides. So it's got to be these two. All right. And describe the necessary steps for proving them congruent using HL. So here we go. So the first thing we say is triangle ADC is congruent to triangle BDC. That's what we're trying to prove. The two triangles congruent. So we're given CD is perpendicular to AB. So both triangle ADC and BDC are right triangles. Yes? Okay. CD is a common side. All right. So they're going with this being congruent to itself. Okay. We could have used these ABs here because it said bisector, but they're using the common side, which is fine. So given ABC is isosceles, AC is congruent to CB. Okay. And then that proves we have a right angle, we have a leg, and we have sides. You could have used the other legs because of the bisector, the word bisector, but they decided to go the other route, which is okay. Let's get that out of the way. Okay, this one's quite lengthy. The opposite sides of a parallelogram are congruent. I'm just going to label this as I go. So I know AB is congruent to CD. I know BC is congruent to AD. Opposite sides of a parallelogram are congruent. The opposite angles of a parallelogram are congruent. So I know that the measure of all of this, ABC, is congruent to angle CDA or ADC. I know that the measure angle BAC is congruent to the measure of angle DCB by this. The diagonals of a parallelogram bisect each other. Well, that means that this side is congruent to this because it's bisecting. And it also means that AE is congruent to EC. So there's all kinds of congruencies going on here. That's why I'm only using one mark, just using different colors, because I should go 3 and 4, but that just gets really messy. All right, so those are the 3 things that we know about parallelograms with diagonals. All kinds of information. So the measure of angle BE, let me just move this out of the way. This is a lot, so I'm going to make it larger because it's hard to see. The measure of angle BEC is congruent to ADE. BEC is right here, is congruent to AED because they're vertical and vertical angles are congruent. BE is equal to DE. Okay, so let me just start over. I just talked about everything, but now they're going in a certain fashion. So they said BEC is congruent to AED. BE is congruent to DE, and angle CBE is congruent to ADE. This is congruent to this. Okay. All right, let me just clean this up a little bit. There we go. So we have, because these are alternate interior angles, because AD is parallel to BC and BD is a transversal, we have alternate interior angles. That's what gives us these 2. Now we can say that triangle BEC is congruent to triangle DEA by angle, included side angle. By similar reasoning, we can show that, and I will go through this one too. Start over. Let's choose a different color. Triangle, similarly, we can say BEA, this triangle over here is congruent to DEC, this triangle here. So we proved this congruent to this. Now we're going to prove this one congruent to this one. Okay. Since AB is congruent to DC, okay, opposite sides of a parallelogram are congruent, and BC is congruent to DA, opposite sides of a parallelogram are congruent. ABCD is a parallelogram because the opposite sides are congruent, property of a parallelogram. Okay, that one was a lot of writing. So let me move that up here. Extend the page so I'm higher. There we go. And the next one, the mid segment of a triangle is a line segment that connects the midpoint of 2 sides of a triangle. The mid segment is parallel to the third side of the triangle and it's half the length of the third side. Okay, so DE, D is the midpoint of BC. E is the midpoint of AC. DE is 12, so therefore it is a mid segment. Okay, and so therefore AB is 14. And so then we can set up ratios, proportions. We know that this triangle here is 1 to 2 with the big triangle, or 2 to the big triangle to the little triangle is 2 to 1. Okay, so it says DE is a mid segment of triangle ABC. DE, mid segment. Find the perimeter of triangle ABC given the labeled segment lengths. Okay. So here's what we're going to do. Okay, I know DE is half of AB by definition. So this is 24, 12 times 2. Okay. But how do I find, if BD is 20, how do I find DC? Well, that's a midpoint right here. So this is 20. E is the midpoint of AC because it's a mid segment. So if AEC is 16, AE is 16. So now I can add up all of these lengths except the 12, because I want the perimeter of the big triangle. And I just say 24 plus 20 plus 20 plus 16 plus 16. 6 and 6 is 12, and 4 is 16. Carry the 1, 2, 3, 5, 7, 8, 9, 96 units. 96 units. Okay, the next one, the three medians of a triangle. Remember what a median is. A median is a segment. A median is a segment that goes from the vertex of a side to the midpoint of the opposite side. So there's a median. Vertex B goes down to midpoint F, midpoint of AC. And finally, start at angle A, go to the midpoint of BC, which is E. They all intersect at the same location. All three intersect at that, okay? So it says the three medians of a triangle are concurrent, meaning they meet at the same place, at the centroid. The location is called the centroid. The centroid divides each median into two parts from vertex to centroid in a ratio of 2 to 1. So AG from the vertex of the angle to the centroid is 2 times the distance from the centroid to the midpoint. So if AG is 12, GE is 6. If FG is 5, now don't confuse these. This is from the midpoint to the centroid, so it's half the distance from the centroid to the angle. So if this is 5, this distance is 10. And if this side to the centroid's 8, centroid to the angle's twice that, 16. Okay, so it says if AE, BF, and CD are medians of triangle ABC, find the lengths of BG, 10, GE, 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 6, and CG, CG, 16. So it's 10, 6, and 16. Hey, where's my answer? There it is. So BG is 10, GE is 6, and CG is 16. Okay, this brings us to the end of lesson 34 and the end of module 1. These last two lessons, 33 and 34, are really good references to a study guide for your unit test. So do the problem set here, lesson 34, and good luck on your test.